Okay, so for decades, our best shot at a theory of everything had this secret, kind of galaxy-sized embarrassment. It was this absolutely beautiful theory that could describe almost any universe you could dream up, except, well, ours.
I mean, that's a pretty huge problem, right? Imagine you have the blueprint for all of reality, but when you try to build the one reality you can actually see, it just doesn't work. That was the exact crisis that was facing string theory.
And we're not talking about some small rounding error here. Back in 1998, when astronomers figured out our universe's expansion is actually speeding up, it sent a massive shockwave through the world of physics. The most popular versions of string theory, they just had no answer for it.
So let's really dig into what this problem was and why it had an entire generation of physicists basically tearing their hair out.
You gotta understand, at its core, string theory is it's beautiful. The whole idea is that everything, every single particle, every force, is just a different note being played by these unimaginably tiny vibrating strings. It's supposed to be the thing that finally unites quantum mechanics and general relativity, the two great pillars of modern physics.
But, yeah, for all of its mathematical elegance, there was this massive, glaring catch. The theory just seemed to stubbornly keep describing the wrong kind of cosmos. Okay, so here's the heart of the problem. String theory was fantastic at cooking up universes that would eventually collapse in on themselves. These are universes driven by a kind of negative, contracting energy. Scientists call them anti-de Sitter spaces. The problem is, our universe does the exact opposite. It's being pushed apart by a positive energy we call dark energy, and it's making the expansion speed up. That makes our home a de Sitter space. So the theory was like a perfect map to the wrong planet. And for many scientists, that was almost a deal breaker. But the solution, amazingly, came from a totally unexpected place. A weird, ghostly effect from quantum physics that was predicted way, way before anyone even knew dark energy was a thing. So check out how all the pieces fell into place. It starts way back in 1948. A physicist named Casimir predicts this truly bizarre quantum effect. 50 years later, 1998, astronomers discovered dark energy, and bam, string theory has its big crisis. Then, just last year, physicists finally connected the dots and realized that old clue from 1948 was the key the whole time. So what is this ghostly effect? It's called the Casimir effect, and it is wild. It basically says that even in a totally perfect vacuum, you can get a real, measurable force generated from absolutely nothing. It sounds like science fiction, I know, but it is a proven, real part of quantum theory. Here's the basic idea. Quantum physics tells us that so-called empty space is actually this bubbling, fizzing sea of virtual particles that are constantly blinking in and out of existence. Now, what happens if you put two metal plates really, really close together? Well, between the plates, only certain little waves of these fluctuations can fit. But outside the plates, you've got all the waves. This imbalance in energy creates a real physical pressure that actually pushes the plates together. It's a force from nothing. It's a crazy thought, right? Could this strange quantum pressure, this literal phantom force, be the missing ingredient that you need to finally build a universe like ours out of string theory? Well, a couple of physicists decided to find out, and what they came up with is one of the biggest breakthroughs the field has seen in years. So meet Bruno Benteau and Miguel Montero. They're working out of the Institute for Theoretical Physics in Madrid, and they're the ones who took this old idea and aimed it squarely at string theory's biggest problem.
And the core of their idea is it's such a beautiful analogy. They realized that the tiny, curled-up extra dimensions that string theory predicts could act just like those metal plates from the Casimir effect. The space inside these extra dimensions is so small that it would naturally restrict those quantum fluctuations, creating its very own inward pulling, Casimir-like force. Okay, but an inward pulling force by itself would just make those extra dimensions collapse into nothing. So they needed something to push back. And they found it in a standard ingredient from the string theory cookbook called flux. You can kind of think of flux as being like the air you pump into a balloon. It creates an outward pressure. By perfectly balancing that inward Casimir pull with this outward flux push, they were able to create a stable universe that wouldn't just collapse on itself. And the result? Well, for the first time in history, physicists had built a precise, detailed model of a de Sitter universe, our kind of universe, with positive dark energy directly from the building blocks of string theory. As the physicist Thomas van Riet said, this was a historic first. It's a huge deal. But of course,
This is theoretical physics, so a huge breakthrough is rarely the final answer. And this brilliant solution, well, it comes with a few important asterisks. A really big part of their success was actually calculating a number for the dark energy in their model. And they got one, a number that was positive and incredibly small, 10 to the minus 15. Honestly, for a first try, that is a fantastic result. It's exactly the kind of thing you'd want to see. However, the actual volume of dark energy that we observe out in our universe is astronomically smaller. It's closer to 10 to the minus 120, a number so vanishingly tiny it's almost impossible to wrap your head around. So while their model is definitely on the right track, there is still a massive gap to close. And there are two other big wrinkles. First, their model works in 5 dimensions, not our familiar 4. That just helps simplify the math. Getting it to work in 40 is the next huge hurdle. And second, the dark energy in their model isn't constant. It's unstable, which means it should get weaker over time.
And this is where things get really cool, because this is just how science works. What seems like a flaw might actually be a feature. Some very recent data from astronomers is hinting that our universe's dark energy is weakening. If those observations hold up, then this model's instability isn't a bug at all. It might be the first clue that it's actually describing reality correctly.
So what does all this mean? Where do we go from here in our quest to figure out the cosmos?
Well, for the first time, we have a concrete, calculable path to connect the elegant math of string theory to the expanding universe that we see all around us. That huge wall between the theoretical anti-de Sitter worlds and our de Sitter reality has finally been breached. Look, this is far from the final answer, but this breakthrough has opened up a whole new frontier, and it leaves us with this really tantalizing question. Are we finally getting our first real glimpse of the universe's source code?